Okay, so the first presentation for this session is the SAM4L technical overview. So during this presentation, we will see, or I will introduce the SAM4L. I will start by explaining what are the design optimization that you can find in SAM4L. These design optimization are mainly focused on what we call energy efficiency. So we will see the general architecture of SAM4L, the clock management, the power management, and the flash controller. Then I will continue with low power techniques, so mainly power saving mode and power scaling mode, peripheral event system and sleepwalking. Then what are the application specific peripheral that you can find on SAM4L? The ecosystem with Atmel Studio 6 and Samba, and I will finish by a short slide which summarizes everything. So please do not hesitate, if you have any question, to interrupt me. I will be pleased to answer. So the SAM4L has mainly been designed for what we call low power project. So when a customer try to design a low power project, he mainly focus on different points. The first one is energy efficiency. So it's really important for you to know what is energy efficiency. So energy efficiency can be defined as is. It's the performance that you've got compares to the power that you invest in your microcontroller. So on this point, a customer's try to find a microcontroller that allows to reduce the power consumption, extend the battery life of his application, and also have fast wake-up capabilities. The second point is non-compromised performance and functionality. The customers really want a powerful CPU with a lot of user interface capability. Next point is the cost efficiency. So we want a microcontroller with high integration in order to reduce as much as possible the bill of material cost. And last but not least, he's looking for a microcontroller that is easy to use. So in order to answer all these points, Atmel have introduced the SAM4L. So SAM4L is the first microcontroller that bring pico-power technology to the ARM platform. So it's the first SAM product with a pico-power technology. So pico-power technology is a continuous power saving innovation. It's mainly at design level. So this means that when we design the chip, we add, or it's designed from the ground up for the lowest possible power consumption. So we add a lot of innovative device features and low power techniques. So you can see this pico-power technology has been introduced with the UC3B in 2007. Then it has evolved in time, and then we are now with the SAM4L with a much more, let's say, with less consumption in active mode, also in full RAM retention mode, and also in backup mode. So it's still improving, and probably in the future we will be also able to reduce again all this consumption in all this mode. So now we can say that SAM4L is the world's most power efficient Cortex-M4 on the market. So it's mainly optimized for a low power application. It's the industry lowest power consumption. So with an active mode, which is down to 90 microamps per megahertz, RAM retention mode, which is 1.5 microamp, and a full range operation from 1.8 volt to 3.6 volt. So we have no degraded performance inside this range of voltage. And then we also have a fast wake up. It's 1.5 microseconds in some low power mode. So we'll see this just after. We also have integrated hardware Q-Touch. So it's, this hardware Q-Touch is also built for low power techniques, as it allows to wake up from deep sleep mode and just with a touch. The next point is that we also embed a segment LCD controller, which can drive up to 4 per 40 segment LCD. So in terms of derivative, the SAM4L is divided in two series. The first one is the SAM4L C series, which embeds mainly the LCD controller, the segment LCD controller, an hardware crypto, a USB, which is host and device. The second series is the SAM4L S, which does not include the LCD, neither the hardware crypto, and a USB, which is only device. If we compare the two series, they are both available from 48-pin package to 100-pin package. In terms of GPIO, we have more GPIO on the SAM4LS. This is because we don't have the LCD controller. And in terms of flash, both of the series are available in with 128 kilobytes of flash and 256 kilobytes of flash. In terms of communication protocol, only the I2C can have different options. It will mainly depend on the pin package. So you can find two master slave, or only two master slave, or one master slave. Any question on this slide? No? So let's start with the design optimization. So first, the SAM4LC architecture. So the SAM4L is mainly built around the Cortex-M4 core from ARM, which is the latest Cortex-M core and the most power-efficient Cortex-M core on the market. So this core communicates with all the peripherals using what we call the multi-layer high-speed bus matrix. So this bus matrix, in fact, have one layer for each master in the device. So all the masters are represented here in green. So this means that if one master wants to communicate with one peripheral, it will have a dedicated layer. And each master have a layer, so it will increase the bandwidth of the system. So in terms of memory, we have 32 kilobytes of SRAM, from 128 to 256 kilobytes of flash, and one pico cache. So there will be a dedicated slide on pico cache. Then concerning standard peripheral, we have all the communication peripherals, such as 4 UART, 1 SPI, up to 4 TWI. So TWI is stand for two-wire interface, so it's I2C. Up to 78 GPIO, 6 timer, 1 ADC, 1 analog comparator, a glue logic. We'll see after what is the glue logic, a DAC, and after, let's say, the other part of the peripheral is what we call application-specific peripheral. So we have all the security features, such as the true random number generator or the IES controller. And we have also the PARC, which is parallel capture, and allows, in fact, the microcontroller to interface with CMOS sensor. We have the LCD controller, the CAT-B, which is the Q-Touch, hardware Q-Touch controller, and full-speed USB, which can act as device or host depending on the series that you have, or the derivative that you have selected. In addition to all those peripherals, we have the system peripheral that mainly manage the clock and the power consumption, so all the low power mode of the system. So that's it for this, let's say, a quick overview of the architecture. Do you have any question on this architecture? Any unclear points? Yeah?
Could you provide additional detail regarding the pico cache?
Yeah, sure.
Some use case where
Yes, it's perfect because this is just after. So yeah, we will see this just after. I will just start by the core, and we'll see after the memory. So concerning the core, we are using a Cortex-M4 core. This core is has mainly been designed for power efficiency. It adds a mainly digital signal processing compared to Cortex-M3. So it's based on Harvard architecture, the ARM v7ME, which is SAM2, use the SAM2 technology and SAM2 instruction. So it's compatible with Cortex-M3. When we say compatible, it means that all the software that has been developed for Cortex-M3 with specific core instruction are compatible with Cortex-M4. Cortex-M4 just includes what we call the instruction superset for DSP and SIMD instruction. So you will have full compatibility between Cortex-M3 instruction and Cortex-M4, but not backward, which means that if you are using DSP instruction or SIMD instruction in your project or in your program, you will not be able to run it on Cortex-M3. Okay? We also have the standard low power mode that you can find on Cortex-M product. Non-embedded interrupt controller, which is called the NVIC, and optional memory protection unit, which is included in the SAM4L. Any question on the core? No? Okay, so first design optimization is the clock management. So SAM4L has a very flexible clock management. It's based on 2 controllers and 1 power manager. So the first controller is the backup system controller. So his goal in the system is to generate the 32 kHz clock, which is the clock that will be used in a low power mode. So this clock cannot be cut or shut down. It's always used and always active in the system. The second clock, which is generated by the backup system controller, is the RC 1 MHz, so mainly 1 MHz clock. The second controller is the system controller. It allows to generate all the other possible main clock sources. So it can be 450 kHz to 16 MHz clock using the oscillator 0. It can be also 115 kHz clock from the SCCs, or 4, 8, 12 MHz clock from the RC fast, 80 MHz clock from the RC 80 MHz, or directly can generate clock from the DFLL and the PLL. So we will see the difference between DFLL and PLL just in the slide just after. So the power manager will in fact take one of these clock as the main clock, and then you will be able to generate, using the power manager, all the system clock, such as CPU clock, AHB clock, which is the system bus clock, and all the peripheral bridge clock. So you can see here that we have 4 peripheral bridge. So this means that we have, let's say, the peripheral are divided in 4. This mainly allows to have a different clock on different peripherals, so you have much more flexibility in terms of clock configuration. Moreover, all of these clock can have different divider, so they can be different, and also can be masked in the system, so that you can mask them in order to reduce power consumption. That's it. One thing to take in account is that CPU, the system clock, and the APB-B, so peripheral bridge B, must be equal. That's it. Yes?
What is the default clock?
The default clock is the LCCs. It's 115 kilohertz. Then, after reset, you can switch on the clock that you want to use.
And which actual clocks are active after reset?
Only the LCCs. So you need.
But is the CPU clock running?
Yes, sure. Yeah, you mean the system clock? Everything is running. Yes. Yeah. Everything is running.
So
then.
If everything's running, don't you have peak current at startup?
Yes, you're right. Let me check, because okay, I know that at least peripheral bridge clock are running. System clock, yes. CPU clock, yes. So yeah, you should have a peak. Yeah. Then after you need to fine tune what you want to do. It's a good question, because we have also another mask system, which allows to mask each peripheral independently. And here So it's divided in a CPU and for all the system clock. And here you can see in black all the clocks that are enabled by default. So yes, if you don't use one of these peripheral in your system, you will have after the reset to mask them. But okay, we have reduced the consumption peak by just enable by default some few peripherals, but not all. Any other question on the clock system?
So could you maybe explain how the clock failure detection is working on the SAM4L?
The clock failure detection.
No such feature.
No, I don't. Yep.
This feature is available on the SAM4L, SAM4E, but you don't have the equivalent on the SAM4L.
On the SAM4L. Is that possible to couple this, or let's say to implement this on the application level and couple such a feature, let's say with a non-maskable interrupt? So I mean to make that.
You mean what? If we have a clock failure,
Yes.
how can we check this?
How can we check this on the application level since we haven't implemented in hardware on the SAM4L?
I think we have probably a frequency meter, but yeah, you will not be able to probe one or to check one clock if you are running on it.
Okay.
So yeah, I don't see any except external chip. I don't see any solution for this. So external chip that will generate an interrupt if needed. Yeah. But that's a good question. Okay, concerning the DFLL, DFLL stands for Digital Frequency Locked Loop. It can be used as in two ways in the system. As a programmable oscillator in open loop, so this is let's say, usage. And the second one is an accurate frequency multiplier such as standard PLL. So it's when you use a closed loop with a frequency tuner. So it's mainly two options that you can select in the DFLL register. So this DFLL can generate 20 to 220 megahertz output. It has an additional spread spectrum option, so it's for better EMC protection. And the main advantage compared to PLL is that it can run from 32 kilohertz clock sources. This is not the case for PLL. And then it allows to have no external component. You can use it for generate a high frequency without any oscillators. The constraint versus the PLL is that the accuracy is there's a drift in the output, 0.5% drift error maximum. So it prevents the use of USB when you are running from DFL. Okay. So that's it for
For the speed spectrum option there, how is it distributed?
That's a good question. I think you have a range. It's automatic, so you cannot select a range of frequency for the distribution. Probably we need to check with design for these things. I know that you cannot change the bands, the frequency band, but yeah, we need to check. Mm. Okay, any question on the clock management? So next design optimization is on power management. So SAM4L has 5 power domains. The first one is the core, so vCore. The backup was vBackup, LCD, GPIO, and analog. What you need to know is that core and backup are supplied by an internal regulator. So this regulator can run from 1.68 volt to 3.6 volt. So the main, let's say, aim of this regulator is that it enables single 1.68 volt to 3.6 volt power supply. It outputs, it's a dual output regulator, so it outputs voltage for vCore and vBackup domain. vBackup domain is always powered, and vCore is not powered. It's automatically shut down when you are entering low power mode. It's, as I said, automatic controlled, so it's fully transparent for the user, and it's enabled automatically after the reset. So it means after reset, the vCore is enabled. So the voltage regulator can work in two modes. The first one is the switching mode, and the second one is the linear mode. The mode selection is done by hardware, so you have a dedicated pin to set in order to select one of these modes. So the selection of this mode is done mainly according to your VDD in voltage in your application. So in fact, those two modes allow us to extend the voltage range of the microcontroller. So this is a feature which is a key feature of the product that no other, let's say, microcontroller have. So depending on the VDD in voltage, you will choose either the switching mode or the linear mode. If you are above 2.3, it's much more efficient in terms of power to select the switching mode. If you are below 2.3 volts, it's much more efficient to use the linear mode. So that's the only thing you need to know. That if you are above 2.3 switching mode, below 2.3 linear mode.
But why is that? Is that just because the power consumption of the
No, mainly yes. It's used to the.
Is that the power consumption of the regulator that makes the difference?
Yes, it's the power consumption of the regulator that makes the difference. In order to go to 1.68 volts and usually below 2.3 volt, you need to use a different method, which is the linear mode. In this mode, if you run in linear mode above 2.3, you will have a lot of power consumption. Same for switching mode. You cannot go, and even here, it's not applicable below. Yes. So mainly, we try to extend this voltage range by including a linear mode also. So as I said, it's a key feature for the SAM4L. So in terms of schematic or bill of material, when you want to use the switching mode, you will have to put a pull up on the pin selection, which is buck LDO, and also an inductor on the VDD out pin. For the linear mode, no more inductor on the VDD out pin, and a pull down in order to select the correct mode on the buck LDO pin. So if I summarize everything in one slide, so this is mainly for power efficiency. So the switching mode is optimum when VDD in is above 2.3 volts. Linear mode is optimum when VDD in is below 2.3 volts. If we take one example, if my application is running at 3.3 volts, so VDD in at 3.3, if I perform measurement, I can see this. In switching mode, which is the appropriate mode, I have 99 microamps per megahertz. If I switch to linear mode and I stay at 3.3 volts, in linear mode I have 208 microamp. So you can see here it's really depend on the voltage. Okay. In terms of bill of material, the switching modes require more external components, an inductor, and you also need a good quality ceramic capacitor for decoupling on VDD core. In linear mode, there are no external components required. In terms of emitted noise, the switching mode requires proper filtering because it's noise sensitive. And for linear mode, it's mainly fits for noise sensitive application. So to summarize, when you have to choose between the two modes of the regulator, it's mainly a trade-off between low power, bill of material costs, and noise sensitive environment. So that's what you need to know. Any question on this subject?
So you can't then run it from a battery whose voltage is dropping and then switch over?
That's a very good question. No, it's mainly hardware. So there is no software way to switch from the two different regulator modes. So the only things, and I tried to have an example, but then nothing is available for the moment, is to drive it by an external pin and try to switch. But I think it's pretty difficult to do this. Yeah.
So in your table, you're presenting your comparing power consumption at
Yes.
VDD in 3.3 volts.
Yes.
It would be interesting to see it at 1.8 volts.
Yes, but okay, I did not provide this because it's not in the datasheet. This is why I would like to stay in something that is in the datasheet. But yeah, that's a good point. Yeah.
So for low power application, do you recommend to use a switching mode at 2.3 volt or the linear mode at 1.8 volt?
For low power application, I would suggest to be in the linear mode because you have no need to be at above 2.2.
Can expect to be below 100 milliamps per megahertz
Yes.
as well?
Yes.
I have another question. I see there's a change in power consumption when you go above 12 megahertz.
Yes.
Is that the regulator that? What's causing that? Is that the regulator's power?
That's a good question. Yes, it's mainly the regulator. We will see this just after because there is another way, also another mode for the regulator that allows to change a bit his output depending on the frequency that will be used in the core. If you are above 12 megahertz, you do not require high voltage on the core. If you are below 12 megahertz, you can reduce the voltage on outputted by the regulator. So mainly the difference comes from here. There will be a dedicated slide. It's not linked. It's not linked to those two modes. It's linked to what we call power scaling method. So we'll see this just after in the low power techniques. Okay, let's continue with the power. So concerning the LCD segments, all the pins, all the segments are divided in three blocks that we call cluster. Each of these clusters have a different, let's say, way to be powered. So it will mainly depend on the usage that you will do for this, the usage that you will choose for this IOs. So it can be fully dedicated to the LCD controller. So it means that you need all the segments. You need to drive 4 per 40 segments on your LCD. So in hardware, you will just have to connect VLCD in to the first cluster. Then all the switch will be done in software so that all the GPIOs will be powered. The second method is when you don't want to use one of the cluster. So in this case, you will have to power VLCD in for the LCD cluster and switch on by software just the cluster B, for example. So you will use cluster A and cluster B. Then for the remaining cluster, which is cluster C, you will have to connect VDD IO. And then all the pins of this cluster can be used as a GPIO. Other configuration is when you want to use only the LCD A cluster. So in this case, you will have to power the LCD A by using VLCD in and the two other clusters with VDD IO. Then there is another configuration if you want to use all the pins with GPIO. So first, it means that you've made a mistake when you select your product, because we have a product that does not embed the LCD controller. But okay, if by the way you want to use this, you can just put VLCD in as the same level as VDD/I/O, and then you will be able to use all the pin as standard GPIO. Any question on this subject?
So is the version without the LCD controllers as
No.
3 VDD/I/O pin?
No. Only this one have this. But that's a good question for the. I mean this one, the VDD/I/O pin.
Yeah.
I don't know. That's a good question. Yes. I don't know. For me, there's only one. But be careful. VDD/I/O level should be the same for all the pin. I need to double check this, but yeah. Okay, so next design optimization is for the flash management. So I would talk about Pico Cache now. So in terms of flash characteristic, we have a single plane 128 kilobyte cache flash, sorry, or 256 kilobyte flash. It's a 64-bit wide access, and we try to, let's say, reduce as much as possible the number of wait states. So we have 0 wait state needed when the core is running up to 24 megahertz, and 1 wait state needed when we are running up to above 24 megahertz up to 48 megahertz. We have an enhanced flash controller that allows to modify what we call the user page. So the user page is mainly a configuration page where you can set store some settings, or even set some bits that enable some specific features in the device. Usually you can find Watchdog, or you can find also some configuration for Samba that we will see just after, or that you will use during the hands-on.
How big is that?
How to use that?
How big is it?
How big is it? I think it starts at this address, and it will go to the end of the
The user page. How big is the user page?
This is a 2 times 32 bit.
Oh, okay. Oh. So in terms of possibility, the flash controller also allows to lock 16 equal size regions on the flash, and you have also a security bit that is in the user page that allows to lock the device for debug access, so JTAG access, or SWD access. So you will not be able to read back the information using JTAG and neither write something.
It's a fuse bit or it's a flash bit? I mean, if I do a full erase.
No, it will not be erased. If you make a full erase, it's a fuse bit. Yeah, it's a fuse bit. As soon as it's set, you cannot reset it. Even with a full erase, I think there is no erase pin on this device. So
for the security bit?
For the security bit, what is the process?
There is a chip erase that you can do through a JTAG.
Yeah, okay, so it's through JTAG.
It's the only way to erase this bit. As there is no erase pin, as Jerome said, there is no dedicated erase pin that can be used to erase the RAM, the flash, the log bits, the security bit. That's different from SAM4L, SAM4E. The only way to erase this security bit is through a chip erase.
Okay.
This is a JTAG or serial wired command.
Okay. And just in case I want to guarantee my customer that he can lock his software and nobody can reuse his software for making or running a fake application, is a lock bit for the flash can be used, or are there also?
You mean the lock bit? The lock bit for this one, it's only for writing, not reading. The only bit that let's say secure the chip is this one, but you will not have JTAG access or SWD. This is why I don't understand that we have in JTAG something that allows to reset this security bit, because JTAG and SWD should be disabled.
It's not directly disabled.
Ah.
The way to access
Is different from a standard
yeah,
JTAG
it's
access.
different,
Okay,
yeah.
perfect.
So it doesn't disable the debug port, it just locks the flash down so that the debugger can't see it.
Yes, exactly, exactly. Any other question on the flash and the flash controller? The next things that the flash control.
Question.
Yes, perfect.
Just while we're on this topic, and in case I forget, if the JTAG is enabled, you're consuming power in the JTAG. Is that not accurate?
You will not consume any power in the JTAG if I think the security is set. But even I think I don't know if there's a way to disable JTAG clock or something like this to ensure that we will not have power consumption. We need to check this. Yeah, we need to check this. I'm not sure that it will.
there is a peripheral in the slide previously.
Yes, I can go back after. Yeah. So next thing that the flash controller can do is enable or disable the Pico cache. So Pico cache is what we call the tight coupled memory, which is really close to the flash system. So his main feature is to compensate the wait state penalty that you have above 24 megahertz. So the Pico cache is made from SRAM technology. So it's 2K, sort of a 2K byte SRAM, which is really close to the flash. As soon as the core will fetch data or instruction in the flash, when the cache is enabled, it will automatically copy the instruction into the cache. Then, for the next time the core requires the same instruction and data, instead of going into the flash, it will go into the cache. So the main interest here is that as the cache is made of SRAM technology, it will not require any wait state, so the core can access it at full speed. And also, the SRAM technology does not require the same amount of power in order to read and data inside. So this means that you will also gain in power consumption, because each time you will access the cache instead the flash, you will reduce the power consumption. Okay, it's not suitable if you are below 24 megahertz in terms of performance, because you will lengthen a bit the process, because you need to copy in parallel. So if it's not needed and you are below 24 megahertz, just disable the cache. Or it's not suitable for a deterministic task to be executed, because we never know when an instruction will be executed. So if it is from the flash or from the cache, the execution time is not the same. So mainly for RTOS or real-time operating system or application, it's not suitable to use a cache, because we really need to know when an instruction and when something is executed. Yes?
Just question, but if you want to have lower power consumption, then you should also use it if you
Yes,
have zero
that's a good question, because yeah, I said that it's not suitable, but only for a performance. If you want to reduce power consumption and you don't care about performance, yes, you can use the cache below 24 megahertz. So when it is disabled, the Pico cache is used as a supplementary or an add-on of the RAM. So you have 2 KB more as RAM. Any question on the Pico cache? You will be able to see, let's say, try the Pico cache, enable, disable the Pico cache if you want in the core mark hands-on. Then you will see directly in terms of performance what is the impact of the cache system.
How much of instruction from the flash is flash to the
2 KB.
in one? So
No, it's okay. That's also a good question. It's okay. The cache is divided in a 4-way, so 4 block. this way, so Frederick will have dedicated slide for the SAM4E on this, but as soon as you will catch or fetch an instruction on data in the flash, it will copy it into one of the way. So then as soon as the way is full, it will go through the second way, and then until the fourth way are full. Then
You copy only the instructions that you are executing, or is it copying?
we have the prefetch buffer in the cache, and we copy the prefetch buffer to this cache system.
It copies the prefetch buffer.
Yes. So it's
The next instruction.
yes. Yeah, it's not only at the instruction level. I think it's a prefetch buffer that it's taken, because we don't have access directly to the flash. We have access to the prefetch buffer. I need to double check this, but I think it's the whole content of the prefetch buffer, not only one instruction.
And you have 60-bit access to the flash in normal mode.
Yes.
So it means that you already fetched 2 instructions.
Yes.
So, and is this 64-bit access cannot be used to, I don't know, avoid to have one-way states?
Yes. Mainly, yes. It's true. Yeah. But yeah, you can avoid this with the 64-bit access. But yeah, I would say that cache system here in the SAM4L is much more for power consumption, not performance. Yeah.
And it will be used if you are executing let's say
Really recurrent code, which means that you are running in a loop, and this loop, for example, fit in the cache, so it will go directly into the cache. So this is you will have no more access to the flash. So as soon as it's like this, yes. But if it's a second shell code, for example, everything is in a block. The cache will be useless because there is no loop, nothing inside. So the cache will be just let's say fulfill then flush, fulfill then flush, and it will be useless. So it's really depend on your code and the way it is optimized. And yes.
Just to add something, for sequential call, as Jerome said, your statement is valid. But as soon as you have loop and branch instruction, then the cache is useful.
Is useful, yeah.
This is only in the case there is sequential call. Then you can anticipate, thanks to the 64-bit buffer, the next instruction. But as soon as you're doing a branch, then you have to flush, and so then the cache is useful.
Any question?
in terms of cache policy, it's a direct map cache.
It's a direct map cache. It's fully
Associative cache.
direct mapped, and it's fully transparent for the user. As soon as you enable it, no need to take care on what is inside. It's just going. It's autonomous. Okay. Any other question on the cache? So probably, or Frederick will also have some other slides on this topic on the SAM4E. Just what you need to know is only the SAM4L allows to have, when disabled, the cache as extension of the SRAM. For in other product, it's not the case.
So you are making the comparison with the SAM4E. So SAM4E has the same.
Yes, yeah, the same cache system. It's not Pico cache. It's cache system. They call this cache in the SAM4E.
And it's the same on the SAM4SA and SAM4SD?
Yes, it's exactly the same IP. Means that at design, on design side, it's the same cells.
But you don't have access to that in SAM4S side.
In SAM4S one,
Yeah.
on SAM4SD32, we have a cache, and it's exactly the same. As soon as you enable it, it will be fully transparent. It's the same system, exactly, but only on SD32 and SA. Yeah, SA. Sorry.
And if you don't enable it, can you still use it as SRAM?
No, not on SAM4SD and SA. Only SAM4L has this. It's mainly due to implementation.
Yeah.
Here, the Pico cache is implemented after the system bus at flash and RAM level. On E and SD, it's above. It's on Cortex M level.
Yeah.
Any other question on the cache? No? So that's it for the design optimization. Now let's talk about our new low power techniques. So in terms of low power techniques, we have two kinds of low power techniques. The standard power save mode, so 4 power save mode, sleep, wait, retention and backup. It's mainly a derivative of the Cortex-M low power mode, so quite all the Cortex-M devices have this kind of power save mode. So you can select one of these modes using a combination of sleep, deep, backup and rotation bit. The second, let's say, mode is what we call the power scaling. The second method is the power scaling. So this mainly intends to scale the power configuration. So this was linked to the regulator. So let's first start with the power save mode. So first mode is the sleep mode. So you can enter the sleep mode by a combination of sleep, deep, backup, retention equal to 0 and the call of wait for interrupt instruction. So this allows a first level power optimization with the fastest wake up time. You have 4 available sleep mode that allows better clock flexibility. So if we focus on clock in this mode, on all this mode the CPU clock is off. Then, depending on the mode, you will have the system clock on, the peripheral bridge clock on, or other clock source running or stop. Then it's up to you in your application to select which mode you want to use. So what you need to know here is that in sleep mode you are wake up, the core is wake up by any interrupt. So in order to generate the interrupt, you need a peripheral, and the peripheral must be clocked. So you have to select the mode that clocks your peripheral. That's it. So depending on the mode and how many clocks are clocked, you will be able to decrease the consumption. Any question on this? I forgot, but we have also the sleep on exit mode. It's a bit. If you enable this bit by software, as soon as the CPU or the core will get the interrupt, it will manage the interrupt using the standard handler, then go back immediately to sleep after the handling of the interrupt. So this is the sleep on exit mode. Second mode is the wait mode. Its entry is done by just setting the sleep deep bit to 1 and keep all the other bits to 0. Again, you can access it using wait for interrupt instruction. So in this mode, all clocks are off except the 32 kHz clock. It's a very low power with SRAM retention and sleepwalking. We will see after what is the sleepwalking. The voltage regulator is in low power, and we have a power consumption of 2.9 microamp in typical. So in this mode, any interrupt from these peripherals allows to wake up the device. So it's mainly 32 kHz peripheral. And in addition to this, you can mask all the peripherals that you don't want to use. So this peripheral will not be clocked, so will not require current consumption or power consumption. The wake-up time is below 1.5 microsecond, and this wake-up time is variable. It depends on the clock that you have selected. So you need to select LC fast in order to have a wake-up time which is below 1.5 microsecond. So you will wake up on LC fast after 1.5 microsecond. Then you can select the clock that you want, but it can increase the wake-up time. Okay? Next mode is the retention mode. So it's really similar to the wait mode. You can see here, if I switch from slide to slide, it's mainly the difference comes from the ultra low power mode. By the way, you enter this by just setting the red bit. So voltage regulator is at ultra low power mode. We have 1.5 microamp consumption in typical. The wake-up time has not changed, so it's below 1.5 microsecond where you are running with AC fast. The only things that is disabled is the sleepwalking. We will see after what is the sleepwalking. And last power save mode is the backup mode. So you enter the backup mode using wait for interrupt instruction, and a combination with sleep deep and backup mode set to 1. So in this mode, all clocks are off except the 32 kHz. It's the lowest power consumption possible, but it requires a restart. So it require this restart because the SRAM is no more powered in this mode. So you lose the SRAM content, then you need to restart as a standard reset, in fact. So in this mode, only few peripherals are able to wake up the device. Again, some of these peripherals can be masked in terms of a clock system, in the clock system, so that you can also reduce the power consumption. Any question on the power save mode? Yes?
Which power supply should you maintain in backup and retention mode?
It's automatically done. In fact, only the in fact vCore is automatically stopped by the regulator, and the backup domain is maintained. So vBackup is maintained, but you need to maintain the VDD in, which is the main power of the. Only the VDD in, and after the regulator do the job.
Because if I try to do comparison with the SAM4S, when I have the vBackup and I can use the supercap or
Yes, it's not the same. Yeah.
it's not the same. So
No.
I have no.
You have no distinction.
additional,
No, you have
vBackup
no.
pin to provide.
No.
Only,
No.
the
Only VDD in. The only ways to do this is to bypass the regulator. So just put your battery or on the VDD in, then power directly the VDD core. If you want to have really a backup system with battery and everything.
And I can leave all the analog input, the LCD.
For me, there is no impact. Or for the LCD, depends if you want to use the LCD in. So yeah, you need to keep only the VDD in this
My
case.
product will stay, I don't know, 2 months on the
Yeah,
shelf
sure.
after calibration of the RTC and.
Yeah, you can just only power the VDD in would be okay. Yes.
In backup mode, the 32K or
Yes.
RC or crystal oscillator.
It depends. You can select in the backup power manager using one dedicated bit which one you want to use. So if you use the oscillator 32K, it will disable the SC32 and reverse.
Yes, but I mean in terms of power domain,
The best one?
in some schematics,
Yes.
it seems that you need VDD ANA to power the.
Ah, yes, you're right. I forget this point. Yeah, probably for the oscillator. Need to check this. I don't know if it's needed the VDD analogic for.
VDD powers the 32K.
Okay. So no, it's needed VDD ANA. Yeah. even the LC32 or both of them. Okay. That's strange. Yeah. Okay.
I have a question to the power consumption. Can you go one or two slides back? On another slide.
This one
There
or the
was
one?
before. Again, there's much higher this top because it's like 1000 microampere.
Yes, but it's higher mainly because you have quite all the clock running except the CPU one. Here you have lower consumption because only a few clocks, the RC6 and oscillator 32 are running.
Compared now to the other ones.
You should have barely the same depending on the. If we compare this to this mode, yeah, you're right. Should be the same. Oh, that's quite high. Yep, you're right. For me, this one should be quite the same as this one because we have only RCCs running. Okay, I need to check this also. Yeah. I need to check this. Yeah. Because I don't know how they perform this measurement. Probably with all peripheral, or I don't know even.
When they are on sleep mode, they have the PLL enabled. I don't know if this maybe not the case in a wait mode.
Yeah. Ah, yeah, okay.
Sleep mode, they enable.
Even you mean even if it's not selected, they are still power the PLL.
Yeah.
Yeah, okay.
You're running at max frequency. So that's the reason you see.
Yes, you're right, and that's the reason that we have the fastest wake up time, because we have a mechanism that switch directly to the maximum clock frequency.
In
sleep
sleep
mode.
mode, you basically just disable the clock of the core. That means that you can choose if you want to have the main oscillator, the PLL enabled or not. And I think we are in the case that the PNL and main oscillator are enabled, so you're running at 48 MHz, just having the core clock, which is disabled. So that's the reason that when you wake up, you will wake up at 48 MHz, so very fast. But that's a trade-off with the power consumption.
Okay, so just to summarize in a table, so run mode is approximately at 99 microamp per megahertz. Sleep mode is at 62, can go down 62.45 microamp. Wait mode is 2.9 microamp. Retention down to 1.5 microamp, and backup mode at 0.8 microamp. So these are, let's say, standard low power mode that you can find in most on the Cortex-M product. The power scaling is another low power technique that you can find only on SAM4L. So it mainly allows to decrease the output of the voltage regulator. So for example, so we have three modes, PS1, which will decrease as maximum the outputted voltage, PS0, which is normal voltage, and PS2, which is a high level voltage. Mainly, when you are running with a core at below 12 megahertz, the core does not require a lot of voltage, the maximum voltage. So we introduce, or we add a power scaling mode 1 that allows to decrease the voltage which is outputted by the regulator, so that you can reduce power consumption if you are below 12 megahertz. If you are above 12 megahertz and in a range of 12 megahertz to 32 megahertz, you can be in a middle range voltage. So you can stay at power scaling equal 0, you will be able to run. Then, if you are running above 32 megahertz, you need to be in the power scaling mode, which is equal to 2, in order to have let's say can be able to run even in the worst case in terms of temperature and everything at full speed. Yeah.
So what is the default?
The default is the medium range, the PS equals 0. Yeah. So then you need to switch.
On your clock level and your system design, you will then switch into the mode.
Yes, you will reset. So you will go directly with PS equal to 0. You will set your clock. Then, depending on the setting, you will move to one from one to the other. The PS2 is not for power consumption. It's mainly for be able to run in the worst case in terms of temperature and.
If we below 12 megahertz.
Yes.
And we're running at a particularly low voltage, and we have PS1 selected.
Yes.
Are there restrictions in terms of temperature, or will it run across the whole temperature range?
It should run across whole temperature range. Yes. So just to give you a short picture of the gain in power consumption that we have when we switch from power scaling 0 to 1, at 12 megahertz, running a prime number algorithm, when we are at in power scaling 0, we have 207 microamps per megahertz. If we switch from power scaling 0 to power scaling 1, then reduce the output voltage of the regulator, we go down to 93 microamps per megahertz. So we have a gain of 52% in power consumption.
And
Yes.
this is only for the core, not for the peripheral. I mean,
It's-
if I have my peripheral
No,
at
it's-
higher frequency for PWM.
It's only for the core, because it's only impact it's a dual voltage regulator, but it only impacts the VDD core output. Only this one. Peripheral will not be impacted because they are supplied by the second line. So it only impacts the core.
So I have to make sure that so then it's clocked by the setting
Yes.
for microphone.
Any other question on this topic?
Any prevention if I set, I don't know, if I'm running the wrong power scaling mode and let's say PSL1 and
You will have.
I change my frequency and
There is no prevention. No. You will see just this system failure. It will not be able to I think to catch the instruction in flash, or even it will be difficult to. Now you need to be careful when you use this. So, as I said, this is a key feature of the SAM4L. A second one is what we call the peripheral event system. So you are probably familiar with this system if you are using UC3 or if you are familiar with UC3. So it's an inter-peripheral communication system that allows peripheral to communicate each other, to send events to each other without the usage of CPU or DMA. So it's a latency-free event handling, so safe fault protection, and it's 100 predictable time. So as there are no interrupts in order to send information from peripheral to peripheral, you have no latency, because an interrupt can be also interrupted due to preemption. And this is not the case in this system. So the advantage is mainly precise timing, it reduces CPU overhead, and also reduce power consumption because the core can do another task or also be in idle mode. I would just give you a short example. If you want to perform a specific acquisition in an application using an ADC, and this acquisition must be triggered by a push button. So we can use, for example, the external interrupt controller to generate an event to a timer counter that will generate also the frequency of the sampling frequency of the ADC. So as soon as you push the button, it will activate, send an event to the timer counter. It will activate the generation of the sampling frequency. Then this generation will send an event to the ADC. The ADC will perform its conversion. Then at each end of conversion, it will send an event to the PDC. The PDC will take the result of the ADC and store it in memory, and also manage the number of acquisition that you will have to do, for example, 256. So after 256 acquisition, it will then send an interrupt to the microcontroller, or to the core. Then the core will be woken up. So all the acquisition system, which means 266 acquisition, will be managed without any core usage, which is really good in this case. So it's really a key feature of the SAM4L, and a key feature when you are developing an application, a low power application. So there's here is a short, let's say, table or matrix that show which peripheral can act as event generator or event user. You will be able to use the peripheral event system in a dedicated answer just after the session. A derivative of the peripheral event system is the sleepwalking. So some of the peripherals that can be used in the peripheral event system allows to act as asynchronous peripheral. So these are called sleepwalking peripheral. So these peripherals are mainly intelligent peripheral. So mainly it's a peripheral that require a clock that is not active in low power mode, such as the ADC, for example. The ADC required a clock which is normally stopped during low power mode. So as soon as the ADC receives an event, it will ask the power managers to enable his clock, just in order to perform the acquisition, then stop it again. So it means that even if the ADC clock, for example, is not enabled during low power mode, the ADC, if the ADC receives an event and is activated, he will require or request his clock to the power manager. The power manager will automatically give his clock. Then it will use the clock for the conversion, then stop it without the CPU usage. So this is also a key feature. In addition to this asynchronous detection, you have also comparison at ADC level or at this peripheral level. The ADC will take, for example, the result of his conversion and check if it is below or above a certain threshold. If it is below or above, you can program it by software. It will wake up or not the CPU. I will just take a short example. It's a temperature monitoring example. My application will go to power save mode with only the asynchronous timer, so it's the RTC activated. This asynchronous timer will generate an event every second. This event will go through will be redirected using the peripheral event system to the ADC. Each time the ADC detects the event, he will require his clock to the power manager. Then it will perform the conversion. If the conversion is below a certain threshold, it will automatically go back to sleep. Then at next event, it will perform again the same thing. The event will go to the ADC. The ADC will require his clock. Then will perform the conversion. If the conversion is above the threshold, it will wake up the CPU, and then we will be able to manage the information and do some task. So again, this is a key feature. You will be able to use it and let's say experiment it in the hands-on. So, but you cannot find any other microcontroller except Atmel one with this feature. So here is the sleepwalking matrix. So you can see compares to peripheral event system, only few peripherals are sleepwalking peripherals. So this is mainly okay. Let's see this ADC, Q-touch, analog comparator, and some of the regulator command. Any question on a sleepwalking or even peripheral event system? No? Okay, just to summarize all the low power techniques. So you have 3 power scaling modes available, which depend on the frequency of your core. In each of these modes, you have available the sleep mode or the wait mode, all the low power mode. So in a concrete application, usually you will go after a reset into this mode. This is power scaling 0. Then you can go into low power mode. What I would say is that if your application is running at 12 megahertz, you will stay in this mode in order to perform all the tasks that you need to perform with the core. As soon as you have finished the task and want to go in low power mode, the best way is to decrease the frequency of the core, then switch to the power scaling 1. As soon as you switch to it, you access to low power mode. Same case if you are above 36 megahertz, so in the range of 36 megahertz and 48 megahertz, you will be in run mode. You will perform all the action, all the tasks that you need to perform. Then you switch the frequency to 12 megahertz or below, and then run into sleep mode. Even if these sleep modes are available in power scaling 2 or power scaling 0, the most efficient way is to play with the clock and go into this sleep mode, because this sleep mode require less power consumption than this one. Okay? Any question?
So we have to make the difference between stopping the clock of the core and reducing the voltage output from the regulator.
Yes. Yeah.
And
It's
PS, the power scaling is really
to optimize the core consumption, the consumption itself, and then you have. Yep. Okay. But even if in low power mode the core is not clocked, it will add a lot of small consumption. So by using the power scaling, you will be able to reduce as much as possible this idle consumption. Okay? So that's it for all the low power techniques and all the design optimization. Let's talk about application specific peripheral. I will try to be quick. First peripheral is the LCD controller. So the LCD controller allows to manage 4 per 40 segments. It has also the capability, a specific feature which is called ASCII character mapping, a segment blink and display blank, and a swap mode that allows to swap pin in order for flexible layout conception. So ASCII character mapping, the goal of ASCII character mapping is to reduce and simplify the software code. In fact, it's a small ROM which is inside the LCD controller and that store all the ASCII character. So it mainly used to, let's say, allow developers to not have lookup table in order to manage the ASCII character. Everything is managed at LCD level. So it will also decrease the display update time so that you will have less software in order to display any ASCII character. And it will also reduce power consumption because you will be able to go back to sleep mode or low power mode in an efficient way. So just for a code example, you just have to select the first segment that you want to use, then with the LCD controller just call the correct ASCII character. Then if I select this segment, it will display 4A7. No need to go to a specific lookup table, check what is the segment I want to drive. It's really easy. In terms of software and power consumption, it will take less time to display an ASCII character. So you will be able to go back to power save mode if you use power save mode much more quickly. So you will gain in power consumption. The second great feature is the segment blink. It's available in sleep and active mode. So it will automatically toggle or blink specific segments. So it can be full LCD or dedicated segments. You have a selectable blink frequency. It will reduce the number of interrupts because it's fully automatic. So no need, if you are in low power mode, to wake up the device, wake up the core in order to just perform a blink. It's automatic and for sure it reduces power consumption. Next peripheral, so application peripheral, is the capacitive touch module. So it's a low power and high performance capacitive touch module, with integrated touch filtering. So it's, yes?
Sorry, I just want to clarify one thing. On the LCD module, we
Yes.
have these features.
Yeah.
Do we have some competitive analysis specifically on competitors' LCD modules? Do they also have similar features?
That's a good question. I think we should contact marketing for this. On our side, we never see any competition analysis on LCD yet.
Okay, it's just to know how we position it.
Yeah.
Okay.
Probably you should contact all marketing. Yeah.
Okay.
So let's go back to capacitive touch module. It allows touch filtering and touch detection without the CPU intervention because this is fully hardware. It's an endless configuration, so you have up to 32 sensors that can be buttons, sliders, or wheels. It has differential or a single-handed sensing operation. It's compatible with peripheral event system and sleepwalking, so you can generate different events, so touch, out of touch, or even generate autonomous interrupts. So, yeah, as I said, it's available in sleepwalking. You will see this in a dedicated hands-on again. You will use the sleepwalking with the Q-touch capability. In order to wake up the device, you will have to push the Q-touch button. In terms of communication peripheral and analog, we have three. I will not enter in detail. A USB, which is 12 megabits per second USB with an embedded host. It will depend on the device that you have selected. What is important on the USB is that we have the on-chip transceiver, so no need to have transceiver in an external component. So it's already embedded in the USB controller. So we have a 12-bit ADC, a 10-bit DAC. Most of these peripherals are compatible with PDC or DMA. Concerning security and flexibility, we have 128-bit AES, 32-bit true random number generator, a hardware CRC and serial number, a UART, a Pico UART. So we call it Pico UART because it mainly adds some low power features such as extended UART wake up capability, a parallel capture. This parallel capture allows to interface CMOS sensor with the device, and a glue logic controller. So the glue logic is mainly used. It's a programmable lookup table with 4 inputs and 1 output on the device. It mainly allows to avoid the usage of external component for a basic operation such as OR, AND, or XOR, for example. In terms of ecosystem, I think that everybody knows Atmel Studio 6. So 3 professional IDEs with the support of all the ARM and AVR Atmel MCUs. Atmel software framework, there is a dedicated Atmel software framework, or let's say Atmel SAM4L is supported in Atmel software framework since the version 3.4.1, and you can find a lot of examples on the SAM4L. Concerning Samba support, Samba on our previous SAM product was stored in ROM, but we don't have ROM on SAM4L, so we change a bit the way to use Samba code. It's now preloaded in SAM4L Flash, so it's a Flash bootloader code. It's compliant with Samba user interface, and it has the same functionality as the standard Samba, so you can communicate with USB or UART. And in addition to the standard Samba, you have the possibility to set some IOs in order to enter or not into Samba boot method. So mainly, it's a software that is stored at the beginning of the flash. So after a reset, you will go directly into Samba boot code. Then, depending on the I/O level that you have selected, you will go into Samba update process. So you will be able to update the firmware of your MCU, or completely, let's say, jump into the application directly without going through the update process. So there will be, again, a hands-on dedicated on this. You will be able to choose if you want to do it or not. Just what you need to know is that if you want to use Samba, so it's preloaded in the flash, you need to lock the first region in order to avoid any corruption of the Samba, and then you can program your application. So just the application must be linked at address 4000. In terms of evaluation kit, we have the SAM4L EK. It embeds a debugger, which is a SAM3X with a Sega firmware running inside. We have a power measurement feature, so it's this part of the evaluation kit. It mainly displays the power consumption. So it's based on again, I think another. Or it's the same product, SAM3X. It's totally independent from the SAM4L part. And concerning the SAM4L part, we have an LCD display, so segment LCD display, USB, which is dedicated to the SAM4L. The second one is dedicated to the embedded debugger. Capacitive touch which is here, one button, one slider. An extension support that is compatible with sensor explain board and wireless extension. And you have also the full support of this board in Atmel Studio 6. So to summarize, SAM4L is the world's most power-efficient Cortex-M device on the market. It's optimized for low power application. It's the industry's lowest power consumption with an active mode down to 90 microamps per megahertz, a RAM retention mode which go down to 1.5 microamp, a full range operation from 1.8 to 3.6, plus an extended range which go through 1.6, but you are limited to 12 megahertz. An integrated hardware Q-Touch, fast wake-up time, integrated hardware Q-Touch, and the integrated LCD controller. So that's it for the SAM4L presentation.